And you're live.
Awesome.
You can start.
All right. Okay. Sorry. All right. So, hello, guys. So my name is Joran. I'm a security researcher at MythX, and well, as you can see, I'll do a talk today about mutation testing. But first, I'll give you a little bit of context about what we can do at MythX. And there's the MythX platform, which kind of allows you to have an easy interface to find bugs and common vulnerabilities in your smart contracts. The second thing that MythX can do is look for violations to properties which you specify using assertions of some sort. And these two aspects contribute in large part to secure smart contract development, which is a topic that we care a lot about. And last year, I wrote a research paper and released a tool called Vertigo, which implements the testing technique called mutation testing. And this is what I'll be talking about today. And I'd like to start out with a question, but unfortunately, feedback is a little bit difficult. So I'm just going to assume that whatever the answer is to this question. So do you use code coverage? And the answer is probably yes. I looked at a few big open source projects, and as you can see, they all report code coverage, and some of them actually pretty high code coverage percentages. 99%, 98%, and this sounds really good, but does it actually mean anything? Does this high score mean that you now trust your test? And well, this is maybe a trick question because, and I'll show you why. So here I took some unit tests from the Metacoin truffle box and removed some statements. And if you look carefully, you see that some of the variables are grayed out, which is a hint to what I removed. And what I removed is code coverage. So the code coverage between these unit tests and these is exactly the same. But the second unit tests do actually test your code. They check for cases, but the initial ones where I remove the assertions don't actually do anything. Now, this is maybe a little bit of an extreme example, but it's meant to illustrate like the importance of the actual assertions and values you used to assert that your test actually succeeded. One thing that might have happened to you, it has certainly happened to me sometime, is that I had an assertion where I compared the expected and the expected value instead of the expected and actual value. So this would actually be the same as if I had not written the assertion at all, which is bad. Of course, this leads to the question, shouldn't I use code coverage anymore? And the answer is no. You should still use code coverage because code coverage is very useful in that it tells you what you certainly don't test. And what's awesome about that is that you can take your code coverage and you know immediately how you can improve your test suite by looking at the parts of the code that you don't cover, and then you write a test for them. The only issue is that code coverage doesn't really tell you anything about the code that you do cover. So you would maybe want some more information about that. And that's exactly what mutation testing tries to achieve. And as you can see on the slide, mutation testing tells you exactly how efficiently your tests detect bugs. And we'll go into how mutation testing tries to answer to give you this information. And the point is that if you know how efficient your test suite is at finding bugs, specific in different areas in the code, then you can also know where you need to improve your test to make sure that your test suite increases in quality and that you're able to capture more bugs or prevent more bugs from being in your code. So the general strategy behind mutation testing looks like this. We start by generating a set of bugs, and we do this using mutation operators, like mutation rules that specifically try to introduce certain kinds of bugs in your code. We end up with an entire set of mutated programs with all these different kinds of bugs in them. The next step, we'll take the test suite you have, run them on each version of the program, each with a different bug, and see if the test suite succeeds or fails. If the test suite succeeds, it doesn't really detect the bug, so we say in this case that the bug survived. If the test suite fails, it does actually find the bug, and it helps you to know like something is wrong. And then we say that the bug is killed. And finally, once we have all of this information, we can find the specific areas in the code that are not yet tested as well as we'd like it to be, and then improve those tests or add tests to get this increased level of quality. And I'll go more into the details of these specific phases. So first, the first phase, generating bugs, is actually called generating mutants. So when we have the original program and we change it to create a program with a bug in it, we apply a mutation, and this mutated program is then called a mutant. And how we apply this mutation is done according to mutation operators, which is basically a fancy name for like a mutation strategy or a set of mutation rules. So in the tool I implemented, we first looked at existing mutation testing tools, specifically PIT, which is a mutation testing tool for Java. And we looked at the mutation operators that they enable by default. We specifically looked at those because they have done some analysis where they found that these mutation operators were most effective and didn't create a lot of so-called equivalent mutations, which we'll get back to later on in the presentation. So there's a whole bunch of mutation operators listed there, and in the next slide, I'll give an example of them. We also implemented 2 new mutation operators to mimic bugs and vulnerabilities that a developer might introduce by accident. And I'll give a brief example for that as well. So here we have some examples of the mutation operator mutation rules. The arithmetic inversion changes like addition operators into subtraction operators, and it's mostly pretty straightforward. I personally really like the modifier removal mutation operator, which basically looks at functions, sees if they have a modifier, and then experimentally removes them to create this mutant. But what this will create or effectively test is it will see whether your test suite actually tests for permission control and authentication, because these modifiers are usually used for this kind of logic, like the only owner operator, as you can see on the slide here. And in doing so, the mutation testing will not only tell you like whether these kinds of bugs are being caught, but also where in the code you're not really looking at for these specific kinds of bugs, which can be really helpful. So the second step will be the mutant evaluation. And as I previously mentioned, you will run the test suite and you can end up with an alive mutant or a dead mutant, but there's a few other states that can happen. So sometimes a mutation changes the program in such a way that it's not, or the smart contract in such a way that it's not valid anymore. In this case, we cannot compile the contract and we cannot even run the test suite. And therefore we say beforehand that it is an error mutant and we won't account for it in the later evaluation. The same holds for timeout, which is a little bit differently. So what could happen actually when you introduce a mutant is that you create a loop that runs infinitely long or for a really long time, and distinguishing between the two is really difficult. So we say that after a certain timeout, we assume that there's an infinite loop and we won't account for it in the evaluation anymore. The last category is in brackets, and I did that because it's not really a category on its own. It's actually a subcategory of alive mutants. And the mutants that we categorize as equivalent are those that don't actually differ in meaning from the original program. So what can happen actually is if you have a mutant, you can change a little bit of the code without changing the actual meaning. And I have a little example of such an equivalent mutant here. So this is the max function from OpenZeppelin Solidity. And as you can see, we changed the comparison operator so that the behavior is different when A and B are equal. But as you can see, when A and B are equal, it doesn't matter which one you return for the maximum value because they are equal, of course. So in this case, we say the mutant is equivalent. And you shouldn't say, like the test suite shouldn't fail on this because it's not a bug, actually. It's just syntactically different code. So once we have this categorization of all the mutants, we can come up with a metric that evaluates the entire test suite. And the expression for this is visible on the slide. And in natural language, this basically tells you what the chance is that your test suite detects a mutant in the code. And if we assume that the mutants that we created represent or are representative of actual bugs, then this number will also tell you what the actual chances or estimate what the chances that your test suite will capture or prevent actual bugs in your code. Of course, 100% mutation score doesn't mean you will never have bugs. Unfortunately, we cannot guarantee such things using just testing techniques. But the nice thing is we can have some guarantees and evaluate the test suite and improve it. So test improvement is the next step. And at the very base, what you can do is ensure that the test suite can only improve in quality and never decrease by adding like a mutation testing tool to your pipeline. But what you can also do is look at the specific mutants that survive and look at the specific areas of the code where these mutants were able to survive, and then add tests so that this was kind of the main theory behind most of the core concepts behind mutation testing. And now I'd like to go into Vertigo, the mutation testing tool I built, how you can use it, install it and everything, and then kind of the current state of it, what the current biggest features are, followed by kind of my roadmap or things I would like to add for usability and performance. So yeah, let's get started with that. I'm assuming most of you would have Solidity and Truffle installed already, as well as Python. And assuming that this is actually the case, the only thing you'll have to do to install Vertigo is run this simple command. Following which, you'll need to set up a test network because, as you might have noticed in the previous slide, we need Truffle. Vertigo is currently built on top of Truffle. In the future, we might extend this, but currently it's just Truffle. And Truffle needs to have the Ganesh network or a test network to evaluate the unit tests you've written. Once we have this test network set up, we also need a target for our analysis. And in this case, Admins will just create a directory and download the contracts for you. We'll also need to adapt the configuration a little bit. Namely, we need to have the network we just spun up. And if your configuration looks a little bit like this, you'll be fine. If you have your own project which you want to run Vertigo on, that's awesome. And you'll just have to add the network you previously created. Maybe you have the network configured already. That would be awesome. But with this network configured, we can start the analysis by running this simple command in the directory where you have your smart contract project, your Truffle project. And you start by just doing Vertigo run, and then you need to specify the network that Truffle is supposed to use for the evaluation. You can use multiple networks, in which case Vertigo will run the test evaluation of the different mutants concurrently, but in this case we'll just use one network. And note that if you use a different name for your network, you obviously need to use that name instead of development, which I used here. So if we run this command, we will get the following results. So as you can see at the top of the slide there, we generated 5 mutants, or Vertigo generated 5 mutants for this smart contract project, and we were able to kill 4 of these mutations, and 1 survived. And at the bottom of the output, you'll be able to see exactly which mutants were alive. And unfortunately, you cannot see the entire code where this mutant was introduced. But this is part of the value transfer of the Metacon contract. And as you can see, we applied a mutation which changed the comparison between the balance of the sender and the amount that's being sent. So this is the sanity check, whether you have enough money to actually perform the transaction. And as you will be able to determine from this, the tests don't actually check the edge case where you have exactly enough money to perform a transaction. And therefore, if we introduce a bug at this edge case, we will not be able to detect it. So let's improve the test so that we will. This is the fix, and I'll start out by saying how the MetaCoin contract in the Truffle box is deployed by default. In its constructor, it will assign 10,000, a balance of 10,000 to the creator. And in this test, the creator sends a transaction to some other account. And initially, or in the base configuration, it will send 10. which is not exactly the same as the balance of the creator, of course. So if we now change this amount to be exactly equal to the balance of the creator, we will trigger, or we will cover this edge case, which was previously uncovered. And if we then run Vertigo again on the test suite, we'll see that we actually do capture this extra, this mutation now and kill it. And so now we have 100% mutation score, which is really good. And by doing this mutation, the cool thing is we have not actually changed the code coverage, but we have improved the test suite by covering an additional edge case of both where the sender has enough money to do a transaction, but also when it has exactly enough to perform a transaction. So I would encourage you to try this out and maybe give me feedback on how I could smooth out certain parts of this process, and especially see if there's points in your test suite that might be improved. And then I'd like to go over to the state of Vertigo itself, and the biggest features that there are right now. And to do that, I want to say something about optimizations and features that could be implemented for mutation testing, specifically optimizations, which can be categorized into two basic aspects. The mutation testing can be optimized to do less work, or it can be optimized to do the work it has to do more efficiently. And this kind of helps put a frame of reference to the rest of the discussion. All right, so I've picked 4 of the features that are in Vertigo today, which I'm most excited about, or which are kind of the biggest features. And the first one is parallelization, or parallel execution of the mutants. So as I mentioned before, you are able to pass multiple networks to Vertigo, and then it will use those different networks. But what it will do is take the different mutants and run your analysis in parallel on the different networks, which speeds up execution a lot. There's basically linear scaling with the amount of processes you use, assuming you have enough cores, of course. And this, this provides major speed ups, of course, if you have a nice machine. The second one is mutant sampling, which is actually a fairly straightforward approach. So what we'll do there is, instead of running the mutation analysis on the entire test suite, we take a sample of the mutations that we've generated and only run the analysis on this sample. So what we'll get is an estimation of the mutation score had we used the entire set of mutants, which has a little bit of variability, so it's not super accurate. But we only have to analyze part of the mutants, and thereby speeding up the analysis a lot as well. So we can do like a sample of 10%, speeding up the analysis 10 times. And there's a balance there between the accuracy you want and the speed that's required. The third optimization or feature, this is actually a feature, is written down as universal mutator here. So universal mutator is another mutation testing project, and what they did is define a generic way of writing mutation rules so that you can easily apply it to different languages. But what it also allows you to do is to do really easy development of different mutation operators and maybe write custom mutation operators. So I'll give a brief example from the universal mutator repo itself of what a mutation rule could look like, or a few rules actually. And these actually would work for solidity. And what I like about this feature is that you can write mutation rules that specifically introduce bugs that are possibly unique to your project. So what you can do is maybe swap out certain function calls, which you think you could be done by accident, and write this as a mutation rule. And then by running the mutation testing using this mutation rule, you'll actually evaluate how good your test suite is at detecting that type of bug. And this is useful both for a developer who's trying to improve their test suite, but also for an auditor who wants to know whether the developers actually checked for certain cases without necessarily reading all the tests and manually exploring all possible mutations. All right, so that's kind of the benefit the universal mutator provides. And the last major feature is compiler equivalence, and this kind of reflects back to the equivalent mutation, which I mentioned more towards the beginning of this talk. So to recap a little bit, an equivalent mutant is a mutant that doesn't actually change anything about the code. And we can use the compiler, so C, to capture some of these. So what we'll do here is take the original program and its mutant and compile them both using solc. So the mutant is applied on the source code level, not on the bytecode level. And once the two contracts are compiled, we will compare the bytecodes. And assuming that solc doesn't have any bugs, we can know that if the two bytecodes are the same, that there is no difference in the meaning between the two contracts, that they are semantically equivalent. And what that means is that we know that there's no actual difference between the two, and that the mutant must therefore be equivalent, or an equivalent mutant. This speeds up the analysis because we won't have to execute or categorize the equivalent mutants anymore, but it also speeds up manually, where you need to go through the alive mutants and then see if they are equivalent or not. So this makes it a little bit more usable in that perspective. All right. So what's next? There's two aspects that I really want to tackle in Vertigo. The first one is optimizations, so speeding up the analysis. To give you like kind of an estimation on the current performance, I've run experiments on projects like Aragon OS and OpenStable and Solidity, where the analysis took between 2 and 4 hours. But I really wanted to be able to speed that up into like 10 minutes or 30 minutes, which is a lot more usable as well. The second aspect is usability, decreasing like setup time and making it easier to use mutation testing using different frameworks other than Truffle, which is currently supported. So different optimizations. Let's start out by going into incremental evaluation. So here the basic assumption is that if you run a mutation analysis in your pipeline or frequently on your code base, between those analyses, the tests that kill certain mutants will stay the same. A lot of things will stay the same, so you might be able to reuse this information. So what we can do, for example, is for one test run, record which mutants are killed by which test, and then for consecutive runs, first run these like killing tests on the mutants if they are still present, and only then continuing with the other tests in the test suite. So here, like the optimal improvement will be that you only have to run one test per mutant, which would create a major speed up. The second optimization is mutant clustering, and what we do here is actually pretty similar to the mutant sampling. So in mutant sampling, what we did is we took a random sample of the mutants. With mutant clustering, we will take a more sophisticated approach where we create different clusters of mutants that are similar. And then from each cluster, we'll select one mutant. And this will allow you to achieve the same benefit of only having to run or evaluate less mutants, but it will be more accurate than just taking a random sample of all the mutants. And the last optimization is called test selection, and this is actually the most straightforward one, where instead of running the entire test suite for each mutant, we will take or code coverage for each test, and then given a mutant, we'll only run those tests that actually cover the mutant. So assuming that you don't have tests that cover the entire contract, that not all your tests cover the entire project all at once, this can also provide major speedups. The only issue here is that, as far as I know, none of the current code coverage, Solidity code coverage implementations do yet support reporting this fine-grained coverage per function. But I believe this is something that's on the roadmap of some of the projects, which is awesome. Then the second aspect, which wants or needs some improvement, is dynamic or usability, or and the first aspect there is again the Ganesh network creation. So as you saw in the beginning of this section on Vertigo, you had to set up a truffle network or a Ganesh network, and we had to configure it in the truffle configuration. And what I'd like to have is a situation where Vertigo will dynamically spin up Ganesh networks and instrument configuration, so that there's basically zero setup necessary to run mutation testing. The second benefit that this will have is that it resolves some issues we have with Ganesh, and which is caused by the fact that Ganesh probably isn't made to run a test suite 500 or 1,000 times on, which isn't all that weird. But during our experiments, we would often create hundreds of gigabytes of data and millions of files, which put a strain on our file system and hard disk, which of course we would like to prevent for common use cases. So dynamic Ganesh network creation will allow us to maybe spin up in-memory databases rather than databases on your hard drive, which will be a big improvement. The second usability aspect is framework expansion. So I mentioned this one before. Right now, we only support Truffle, but there's a few really nice projects out there that are gaining more adoption, like Brownie and Bark, which I would also like to support so that more developers can actually use the tool, and the tool would become more accessible. So, in conclusion, I talked a little bit about mutation testing theory, the generation, evaluation evaluation of mutants, and how you can use it to improve your test suite. Then I talked a little bit about Vertigo itself, so the tool implementation, how you'd be able to install and use it, the present state of Vertigo, what kind of features we have right now, and the lowest hanging fruit and the roadmap for Vertigo in the future. And with that, I'd like to end this presentation and thank you all for listening. I think there will be some time for questions, but we'll have to figure that out a little bit, how to do that using Zoom.
Yeah, thank you. We'll try to do some question. Do you hear me?
Yep.
So, does anyone have any question? If you do, I'm just going to ask you to come here to ask it, to have it recorded, and for John to be able to hear you.
Could you repeat that, sorry?
It seems there's no question.
Oh, okay.
So
That's
thank
fine.
you very much. We're going to have the next talk with Bernard, who was consulted before. So we're just changing the schedule. So if you want to stay after this one, you can. There's something. It's not expected, but that's something for you. Thank you, Joran.
No problem.